Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about heterocyclic chemistry. So let us start very basic of heterocyclic compounds from very basic, bottom of the heterocyclic compound. So heterocycles contains one or more heteroatom in a ring. Look at here. This is carbocycle. There is no heteroatom. Carbocycle. Only cycle of carbon. And this is heterocycles. Apart from carbon, some heteroatom, oxygen, nitrogen, sulfur usually. You can see di-substituted and two heteroatoms. Here three heteroatoms like this. Now understand the meaning of heterocycle. Aromatic or partially or fully saturated, this course will focus on aromatic systems. I will discuss on aromatic. So, classification of aromatic 6-member ring. Look at here, isoelectronic carbocycle. This is isoelectronic cycle. And derivative of this, all are 6-member. Here 1 nitrogen, here 2 nitrogen, 2 nitrogen, 2 nitrogen, here 1 oxygen. So pyridine, beryllium, pyridazine, pyrimidine and pyrazine. Now you have this naphthalene and this is quinoline and isoquinoline. Now aromatic 5-member heterocycles. Look at here. Isoelectronics carbocycles. Only carbon cycle is here. And this is heterocycle. Pyrols, furan, thiophene, imidazole, oxazole, thiazoles, pyrazoles, isoxazoles, isothiazole. So you can see these carbocycles and these heterocycles. Now you can see the classifications: unsaturated and saturated. Unsaturated, 4-gamma pyron, this is oxygen, and aromatic dipolar resonance form. Here O plus, O minus. So my friend, you can see here 4-gamma pyron, aromatic dipolar resonance form. Now at the second position, 2-pyridone, it is also dipolar, here positive and negative. Now saturated, ethylene oxide, THF tetrahydrofuran, 1,4-dioxanes, pyrrolidine, dihydropyrin. Now functional group chemistry. Functional group chemistry here, imine formation. Imine formation. You can see the formation of imine. Yes. This is ketone react with primary amine. It is forming imine. It is undergo reactions in equilibrium in acidic medium, forming this positive charge, and then you can see here the mole of water, and then it is equilibrium in this form, and this is equilibrium in this form. So the mole of water is usually required to drive the reactions to completions. If a dialkyl amine is used, the iminium ion that is formed can lose a proton and an enamine is formed. So take page and paper and write it down all in a step by step. Then you will understand very easily. Enols and enolate. You can see the enol form is favored by a conjugating groups CO2R, COR, CN, NO2, etc. Avoid confusing enols generated under neutral or acidic condition with enolates generated under basic condition. Enolates are nucleophilic through carbon or oxygen but react with carbon electrophile through carbon enol ethers. Look at enol ethers, acetyl and carbon double bond oxygen with oxygen has positive charge. Now Inamine, iminium base. Look at here, analogous of enol but are more nucleophilic and can function as enolate equivalents. Removal of water by distillation or trapping drives reactions to compositions. Enamines react readily carbon nucleophiles at carbon. The reactions at nitrogen is possible but usually reverse. Now functional group chemistry, you can see the carboxylic acid, amides, imidine, urea, guanidine and beta diketone, beta ketoester. Building block for sulfur containing heterocycles. So heterocycle synthesis required carbon, oxygen and carbon nitrogen bond formation using imine, enamine, acetyls, enols, enol, ethers, carbon-carbon bond formation using enols, enolate and enamine. During heterocyclic synthesis, equilibrium is driven to the product side because of removal of water, crystallization of product and product stability, which is aromaticity. Now important point is here, general strategy for heterocyclic synthesis. Ring construction. Cyclization, 5 and 6 member ring are the easiest to form. CX bond formations required a heteroatoms nucleophiles to react with a carbon electrophile. So look at here the conjugate addition, manipulation of oxidation state, hexahydro to tetrahydro, dihydro and aromatic. Unsaturation is often introduced by elimination, example dehydrations, dehydrogenations. So general strategy for heterocyclic synthesis 4+1 strategy. Here 4 means carbon, X for heteroatoms. The formations of pyrrole, formations of imidazole derivative. 5+1 strategy is formations of pyridine. You can see 5 carbons containing 1,5-dicarbonyl compound and nitrogen source is ammonia. This is also known as macule additions of ammonia. General strategy for heterocyclic synthesis 3+2 means 2 carbon and coming from different size and 3 from difference. So you can see the dipolar compounds. 3+3 strategies means 3 atoms coming from different parts and 3 from different parts. So look at here the formations of these compounds. Take page in papers and write it down. Now bioactive pyridine, nicotine contains pyridine, sulfapyridine contains pyridine. Nicotine is pharmacologically active constituents of tobacco, toxic and additive. Sulfapyridine is a sulfonamide antibacterial agent, one of the oldest antibiotics. You can see the paracate and isoniazide. Paracate contains here nitrogen positive and positive charge and it is countered by the other molecule, other counter. Paracate is one of the oldest herbicides, toxic and non-selective. Isoniazide has been an important agent to treat tuberculosis, still used, but resistance is a significant and growing problem. Drug containing a pyridine, name Nexium, you can see pyridium, Acifex. So disease acid reflux and disease duodenal ulcers and acid reflux. Now Actose and Gleevec, type 2 diabetes and chronic myeloid leukemia. See the pyridine structure and their directions of dipole moment. Isoelectronic with an analogous to benzene. Stable, not easily oxidized at carbon, undergoes substitution rather than additions. Minus I effect, inductive electron withdrawal, and minus M effect, both working in case of pyridine. Weakly basic, lone pair is not in aromatic state. Pyridinium salt are also aromatic. Ring carbons are more delta positive than in parent pyridine. Look at here. Now pyridine synthesis, hence synthesis 5+1 strategies. Look at here. The 4 carbon and 1 nitrogen coming from different source. The reaction is useful for the synthesis of symmetrical pyridines. 1,5-diketone intermediate can be isolated in certain circumstances. A separate oxidation reaction is required to aromatize the dihydropyridine. Now look at here pyridine synthesis. From enamine or enamine equivalent quadratious synthesis 3+3 strategies. Formations of pyridine 73%, and another side you can see the formations of substituted tetrasubstituted pyridine with keto groups. So beta cyanoamide can exist in the enol form. Using cycloaddition reaction 4+2, you can also get 70% substituted pyridine. Oxazole are sufficiently low in aromatic character to react in the tail center reaction. Now look at the pyridine's electrophilic reactions. Pathway for electrophilic aromatic substitution of pyridine. Look at here the pyridine alpha, beta, gamma positions and their resonative form. The position of equilibrium between the pyridine and pyridinium salt depends on the substitution pattern and nature of the substituents, but usually favor the salt. Now pyridine's electrophilic reaction. Regiochemical outcome of electrophilic substitution of pyridines. Look at here. The resonance formed with positive charge on nitrogen, that is 6 electrons, are very unfavorable. The beta substituted intermediate and the transition state leading to this product have more stable resonance form than the intermediate's transition state leading to the alpha gamma products. Now pyridine electrophilic reactions. Regiochemical outcome of electrophilic substitution of pyridinium ions. Look at here alpha, beta and gamma. Look at all structures. Then you will find at positions 2, 5 and 4 have the positive charge. The radiochemical control is even more pronounced in the case of pyridinium ions. In both pyridine and pyridinium salt, pyridinium system, beta substitution is favored, but the reaction is slower than that of benzene. Reaction will usually proceed through the small amounts of free pyridine available. Look at N substitutions with pyridine. Carbon substitution, reaction at carbon is usually difficult and slow, requires forcing conditions. Fatal graph reaction are not usually possible on free pyridines. Nitration of pyridine at 3 position only 6%. Use of activating groups, then you will get 90%. Now multiple electron donating group accelerate the reactions. Both the reaction proceed at similar rate, which indicate that protonation at N occurs prior to the nitration in the first case. Pyridine electrophilic reaction. Sulfonation of pyridine. You can see at 3 positions and an HgSO3. Low yield from direct nitration but good yield via emerging intermediates. Halogenation of pyridine. Forcing reaction conditions are required for direct halogenation. Now full or partial reduction of pyridine. Look at here. H2 platinum, acetic acid reactions, and then NaNH3. You know the Birk reductions. You know pyridines generally resist oxidation at the ring carbon atom and will often undergo side chain oxidation in preference to oxidation of the ring. So full or partial reductions of ring is usually easier than the case of benzene. Look at the regiochemical outcome of nucleophilic addition to pyridine, and look at each structure. Nitrogen acts as an electron sink. Beta substitution is less favored because there are no stable resonance formed with the negative charge on nitrogens. You can see this and this. Aromatic is regained by loss of hydride or leaving groups or by oxidations. Pyridine nucleophilic reactions. Nucleophilic substitution. You can see the pyridine nucleophilic reactions favored by electron withdrawing substituents that are also good leaving groups. The position of the leaving groups influence reactions rate, gamma greater than alpha greater than beta. So relative rate, you can see 80% para, 40% chloropyridine, and 2 chloropyridine, and 3 into 10 to the minus 4. Now nucleophilic substitutions, you can see the conversion of pyridine into the pyridinium salt greatly accelerates substitution, and substituents effect remain the same. Look at here, and then again look at the relative rate, and that is very important. Take the pen and paper, write it down. If you write, then you will understand what is here. Substitution via an intermediate pyridine, pyridine. See the pyridine like benzene. When very basic nucleophiles are used, pyridine intermediate intervenes. Pyridines are similar to benzenes and are very reactive, not isotopy. Nucleophiles attack with the transfer of hydride. Look at here with Bewley. A hydride acceptor or oxidizing agent is required to generate aromaticity. The reaction with the lithium amide amine is referred to as the Chichi-Bevin reactions. Now direct exchange of metal as a halogens. So halogenated pyridines do not tend to undergo nucleophilic displacement with alkyl lithium or alkyl magnesium reagents. So metallated pyridines behaves like conventional Grignard reagents. Look at here. The use of direct groups, you can see LT MP, LIT MP, which is analogous to pyridine. Direct groups allow direct lithiation at an adjacent position. A Lewis basic group is required to complex the Lewis acidic metal of the base. Now look at oxypyridine structure. Zwitterions, and zwitterions. So subject to tautomerialism. Alpha gamma system differ from the beta system in terms of reactivity and structure. In alpha case, the equilibrium is highly solvent dependent, but the keto form is favorable in polar solvent. Now look at aminopyridine system. Contrast with the oxypyridines. Aminopyridines are polarized in the opposite direction to the oxypyridine. So look at here oxypyridines, electrophilic substitutions. Reactions such as halogenation, nitration, sulfonation are possible. N is more or less basic than that in the simple pyridine. Substitution occurs ortho or para to the oxygen substituents. So look at here nucleophilic substitutions with the PCl5 with different state, how chlorine phosphorus bond will form, and then breaking of carbon oxygen, and then you can see the structure of pyridinium solid. Replacement of oxygen substituent is possible. In this case, the reaction is driven by the formations of very strong phosphorus oxygen bond. Now cycloadditions. Oxypyridines have sufficiently low aromatic character that they are able to participate as dienes in Diels-Celter reaction with highly reactive dimer field. Look at deprotonation with a strong base. Deprotonation of alpha and gamma alkyl groups proceed at similar rate, but beta alkyl groups are much more difficult to deprotonate. Bases are also potential nucleophiles for attack of the ring. So it it is also very important. Now, nucleophilic attack with the reducing agents. Look at here with the difference. Nucleophilic attack is much easier, already seen this. Deprotonation of alkyl substituents is easier, weak bases are suitable. Ring opening is possible by attack of hydroxide. Look at here how pyridine rings is open. N-oxide formation you have already seen. The reactivity N-oxide differ considerably from the pyridines or pyridinium salts. A variety of peracid can be used to oxidize N, but MCPBA is used most commonly. N-oxide formation can be used to temporarily activate the pyridine ring to both nucleophilic and electrophilic attack. Now, electrophilic substitutions. N-oxide is activated to attack by the electrophiles at both the alpha and gamma positions. Nitration of N-oxide is easier than nitration of the parent pyridine. You know, my friend, reactivity is similar to that of pyridinium salt. In many cases, nucleophilic attack, deprotonation of alkyl groups, etc. Take page and paper and write it down this scheme. And look at each steps, how electrons direction is moving, and care about your directions. Now, removal of oxygens with the triphenyl phosphine, you can see. Deoxygenation is driven by the formation of very strong PO bond. Pyridine synthesis of natural product. Synthesis of pyridoxine, vitamin B6 using Pyridine synthesis. Look at here. The final sequence of a step involves formation of this diazonium salt from a diamines. Pyridoxine perform a key role as a coenzyme in transminase. So, bioactive quinoline, isoquinoline, you can see the quinine and chloroquine. Quinine is an antimalarial natural product isolated from the bark of the cinchona tree. Chloroquine is completely synthetic antimalarial drugs that has the quinoline system found in the quinine. Parasite resistance is now a problem. So, Papavirin is an alkaloid isolated from the opium poppy and is a smooth muscles, relaxant and coronary vasodilator. Now, drug containing aquinoline or isoquinoline. Name Singulair, Quinpril and hydroxychloroquine. Look at the structure, all three structure contains quinoline. Now, malaria, approximately 500 million cases of malaria each year and 1-3 million deaths. So, disease is caused by protozoan parasite of the genus Plasmodium, Falciparum, Vivax, oval and malariae. Disease is spread by the Anopheles mosquito female. Now you can see the cinchona tree. You see. You can see the Anopheles mosquito, Plasmodium monocycle. Now, Aquinoline synthesis. The structure of quinoline you can see similar to that of pyridine. Possess aspect of pyridine and naphthalene reactivity. Example: N-oxide and ammonium salt. COMS synthesis in many steps. Write it down in your notebook. Practice it. Practice. You can see in the quinoline synthesis. Conard Limpach Nord synthesis. Very similar to Combase synthesis by beta-ketoester is used instead of beta-diketone. Altering the reactions conditions can completely alter the regiochemistry outcome. Starting from aniline. You can see already, the 3+3 scrap synthesis. Acrolein can generated in situ by treatment of glycerol with the concentrated sulfuric acid. Mild oxidant is required to form a fully aromatic system from the dihydroquinone. Friend, Lander synthesis, write it down. The starting acyl aniline can be difficult to prepare. Acidic and basic conditions deliver regio isomeric products in good yield. Isoquinoline synthesis, you can see the Pomerange fringe synthesis, Bichler-Naplinski synthesis. Cyclization can be accomplished using phosphoryl chloride and phosphorus pentachloride. Oxidation of dihydroisoquinoline can be performed using mild oxidants. Take page and paper, write all the reactions. Isoquinoline synthesis, you can see Pictet-Spengler synthesis, 5+1 strategy. An electron donating substituent on the carbo-aromatic ring is required. A tetrahydroisoquinoline is produced and subsequent oxidation is required to give the fully aromatic isoquinoline. Now, electrophilic reactions. Regiochemistry, you can see at aromatic and at in case of naphthalene. Under strongly acidic condition, reaction occurs via the ammonium salt. Attack occurs at the benzo rather than heterocyclic. Reactions are faster than those of pyridine but slower than those of naphthalene. Nitrations, you can see the fuming nitrations. In case of quinoline, equal amounts of 5 and 8 isomers are produced. Now sulfonations, you can see. Halogenation is also possible, but product distribution is highly dependent on conditions. It is possible to introduce halogens into the hetero rings under the correct conditions. Fidelgraph alkylation acylation is not usually possible. Regiochemistry, you can see attack occurs at the heteroatom rather than benzene. So they are generally more reactive than pyridines to nucleophilic attack. Carbon nucleophiles. Now you can see the oxidation is required to generate aromaticity. Reactions of isoquinoline with the bully. Eminations, 60% yield of thermodynamic product. Displacement of halogens with the quinoline and isoquinoline. You can see the reactions on nitrogen center. Proton adjacent to the cyano group is extremely acidic. The reactions work best with the highly reactive alkyl halide. Now you can see in case of isoquinoline, this is cyclization achieved by the Pictet-Grams reactions and Bichler-Naplinski reactions. Bioactive furan, pyrols and thiophene. You know ranitidine? Ranitidine is one of the biggest cell-killing drug in history. It is an H2 receptor antagonist and lower stomach acid level used to treat stomach ulcers. Ranitidine. You can see the ketorolac. Ketorolac is an analgesic and anti-inflammatory drugs. Banmint. Pyrantel is an anthelmintic agent and is used to treat worm in the leaves stalks. So, Plavix, nitrofurantoin, Cymbalta and Lipitor. So, furan, pyrrole and thiophene structure. You can see 6pi electron planar aromatic isoelectronic with the cyclopentadienyl anion. Resonance structure, you know, electrodonation into the ring by resonance but inductive electron withdrawal. So in case of oxygens, same direction with the sulfur, and in case of pyrrole and unsaturation is different. Saturation is different. Oxygen and sulfur are more electronegative than N, so inductive effect dominate. Now you can see the Paul knot synthesis already I have made. Furan, you can see the fished binary synthesis. Product prior to the dehydration can be isolated under certain circumstances. Reaction can be tuned by changing the reactions conditions. Now modified fished binary. Iodide is better leaving group than chlorine and the carbon become more electrophilic. The Paul knot sequence is followed from the 1,4-diketone onward and regiochemical outcome of the reaction is completely altered by the addition of iodide. Now you can see the thiophene, you know this reactions might occur via the 1,4-bis thioketone. Pyrrole synthesis, I am not going to details. Nor pyrrole synthesis, you can see problem can be overcome by storing amino carbonyl compound in a protected form. So reactive methylene partner required so that pyrrole formation occurs more rapidly than dimer formation. You can see the formation of pyrrole with the different reaction scheme, one-pot oxime reductions and pyrrole formations, Hence synthesis. The modified versions of fished binary synthesis using the same starting material and alpha halocarbonyl compound in beta ketoester. Furan, pyrroles, thiophene, electrophilic substitutions situation. The pyrrole greater than furan, greater than thiophene and benzene. Thiophene is the most aromatic in character then undergoes the slowest reactions. Pyrrole and furan react under very mild conditions. My friends, alpha substitutions favored over beta substitution. More resonance form for intermediate, and so the charge is less localized. Also applies to the transition state. Some beta substitution usually observed depends on X and substitution. Now look at the reactions. Already I have discussed a lot. You note that the brominations of furan, electrophilic substitutions related to furan, with mere formulations. You can see the manic reactions with the furans, synthesis of thiophene. You can see the pyrroles, again reactions of pyrrole, a lot of reactions. You can see the extended aromatic 8 pi electron system is more stable than the having 4 isolated aromatic pyrroles. Now you see the porphyrin natural products, heme, chlorophyll A. The pigment heme is found in the oxygen carrier hemoglobin. Chlorophyll A is responsible for the photosynthesis in plants, and both heme and chlorophyll A are synthesized in the cell from porphobilinogen. You can see the metallations, you can see the deprotonation of pyrroles. So I have already made pyrroles, thiophene on video. Go through that video. I am not going to details here. Just see the furfural is produced very cheaply from waste vegetable matter and can be reduced to give the commercially available compound furfuryl alcohol. The second chain is introduced using the manic reaction, which allows selective substitution at the position 5. The final step involves conjugation addition of the amino to the alpha-beta acetonitrile compound and then eliminations of methane thiols. You can see the tryptophan, you can see sumatriptan and lysergic acid diethylamide LSD. So tryptophan is one of the essential amino acid and constituents of the most protein. Sumatriptan is a drug used to treat migraine and work as agonist for 5-HT receptor in the CNS. LSD is potent psychoactive compound which is prepared from lysergic acid and alkaloid natural products of the ergot fungus. So you can see the indole lysergic acid, the beggars, the creepers by Peters, Bugale, the elders in Paris. Now drug containing anindoles. You can see Imitrax, Calis, Maxalt and Railpax. Now look at the indole synthesis, Fischer synthesis already I have discussed. The protic acid or Lewis acid can be used to promote the reaction. Look at the indole, Bischler synthesis of indole. Alpha aryl aminoketone is cyclized under acidic conditions. The reaction also work with the acetals of aldehydes, nitrations of indoles. Polymerization occurs when there is no substitution and position 2. Halogenation is possible, but the product tend to be unstable. Now acylation of indole, you can look at here. Indoles electrophilic substitutions Manic reactions is very important, a very useful reaction for the synthesis of 3-substituent indoles. The product gramines can use to access variety of other 3-substituent indoles. So I have already made one video about indoles. Go through the details step by steps. Now 1,3-azoles, bioactive 1,3-azoles. You can see O-methyl half-frondinols, vitamin B1, thymine, and cimetidine. O-methyl halofornidol is a plant-derived alkaloids. Vitamin B1, thymine is essential for carbohydrate metabolism. Deficiency lead to beriberi disease, which is characterized by nerve, heart, and brain abnormalities. Cimetidine is an H2 receptor antagonist which reduces acid secretion in the stomach and used to treat peptic ulcer and heartburn. Now, drug containing 1,3-azoles, you can see Mirapex, Azathioprine, Norvir, and Kozar. Now synthesis, enhanced synthesis, you can see 1,3-azoles, a lot of reactions, 1,3-azoles electrophilic substitution. You know, imidazoles are much more reactive to nitration than thiazoles. Imidazoles usually nitrate at the 4th position and thiazoles tend to react at the 5th position. Oxazole do not generally undergo nitrations. You can see here 1,3-azoles do not undergo fatal craft because complexation between the Lewis acid catalyst and N activates the ring. Look at oxazoles, thiazoles, all are 1,3-azoles. 1,2-azoles like leflunomides and silicosics. So leflunomides inhibits pyrimidine synthesis in the body and is used for the treatment of rheumatoid arthritis and psoriatic arthritis. Silicosib is a non-steroidal anti-inflammatory used in the treatment of osteoarthritis, rheumatoid arthritis, acute pain, painful menstruations, and menstruation symptoms. Now you can see 1,2-azole synthesis. This is very important. This is the most widely used route to pyrazoles and isoxazole. The dicarbonyl components can be beta-ketoester or beta-ketoaldehydes. When beta-ketoester is used, pyrazolone and isoxazolone is formed. So look at 1,2-azole synthesis 3+2 scheme. Nitrile oxide react readily with the alkenes and alkynes. Addition to an alkenes generate an isoxazolines unless a living group is present. So look at 1,2-azoles. Pyrazoles and isothiazoles undergo straightforward nitrations. 1-nitropyrazole formed in good yield by treatment of pyrazoles with the mild nitrating reagent, acetyl nitrate. You can see the reactions. Halogenation of isoxazole, pyrazoles and isothiazoles. So direct metallation of isoxazole, pyrazoles and isothiazoles. These two reactions are also very important. You can see the metallations with Gulli. So weak base can use to deprotonate 5-methyl isothiazoles and 5-methyl isoxazoles. In this case, above dehydrations of the initial product occurs in situ. So write it down, a lot of information. Silicosib, you can see the structure of silicosib. So my friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel, and thanks for watching.